Alright, now to our answers here. So what we should have is 3 products drawn where we've carefully analyzed which diethyl tartrate we've been given. Minus is going to approach from the top, plus from the bottom, minus from the top. And then you got to be careful how you draw the orientation of atoms, right? I mean, obviously these are trans to each other, so they're still going to be trans when we draw them on our product. Things that are cis to each other, you want to make sure you draw those cis when you draw your product. So, you want to be careful with your 3D drawings, and also always make sure that you're getting your kind of orientation, kind of this carbon, put that in the bottom right. Now, if you're Googling around looking at other kind of ways to do this or practice problems, you'll see that some folks will put this instead in the top right, and then everything's backwards as far as what ends up on the top and the bottom. Your book picks this way to remember it, and so I decided to be consistent with your textbook. Again, it's just a mnemonic. You just have to always set up your starting material in the right orientation in order to be drawing the correct enantiomer that's formed, given the specific chiral catalyst that you're using. Alright, so I just wanted to go through these, make sure you can draw these nice and cleanly. You can create, 2 chiral centers on these guys. You're going to create usually at least one, right? If everything else was a hydrogen, you'd still be creating one there. So what happens is there's no mechanisms you have to draw for these because it's kind of unknown. It's a proposed catalytic structure. I'll show you that from your textbook. Again, it's just a great reaction, winning the Nobel Prize, cheap reagents, consistently giving good results. You can mess with the groups. The substituents, the enantiomeric purity gets a little lower when you've got the Z or cis type alkenes because of crowding, they think, because the catalyst is pretty big. So in your textbook on page, are you ready for this big old book here that I lugged home? I wonder if we're focused. Yeah, kind of. Page 946. The titanium isopropoxide forms a catalytic structure with the ester. So you can find the ester pieces around here. Okay. So it forms kind of a dimer, but with all the isopropoxides, sometimes it's called a tetramer. But, 2 of these pieces essentially come together. And then what happens, depending on the stereochemistry of your ester, here we've got things kind of coming out at you, the approach of your allylic alcohol and your oxidant is kind of locked in. If we think of this as a big clamp, these things can only approach from a certain face. So here is the oxidant and the alcohol, right? The piece we're going to form our epoxide right here. There's the O, that's going to become your epoxide O, and they get lined up on a particular side depending on the diethyl tartrate ester that you use. So again, this is all proposed. You don't have to draw any arrows. I will not ask you to draw these pictures, but just, have an idea of which O ends up on your molecule, that these are called chiral catalysts, so and be able to draw the products. Okay? That's it for the Sharpless epoxidation.